So in the previous video, I had shown you the solutions of the Schrodinger wave equation for a particle in a ring. The solutions are F is equal to n sine m phi and F dash is equal to n dash cos m phi and F double dash is equal to a exponential plus or minus I m phi. Okay, these were the solutions of the Schrodinger wave equation for the particle in a ring. And now we have m here in these equations. These are these trigonometric forms. These are the real sets, and these are called as circular harmonics. Circular harmonics. And this is an imaginary set. This one is imaginary set because it contains I. And we have to find out the value, the possible values of m in these equations. For that, we are going to bring a condition. The condition is that since f or f dash or f double dash, these are the solutions of the Schrodinger wave equation, or these are the wave functions, the wave function must be well behaved. A well behaved wave function must be single valued. Single valued. You have already learned this in the previous semester. Single valued wave functions. Here we can apply the condition of the single valuedness for a point in the ring. Let that point be represented by 0 and 0, phi and phi plus 2 pi. Because phi and phi plus 2 pi will represent the same point in the ring. It means that the particle is at phi angle from the x-axis, and once it completes a 2 pi rotation, it will reach back the same position, right? So phi and phi plus 2 pi will represent the same point in the ring. So the condition for the single valuedness will tell us that f of phi should be equal to f of phi plus 2 pi. So if f of phi is equal to f of phi plus 2 pi, then it will be single valued, and this condition is must for a well behaved wave function. So it means that if we are taking f is equal to n sine m phi, the solution of the Schrodinger wave equation, then it implies that sine m phi must be equal to sine m phi plus 2 pi. It means that sine m phi is equal to sine m phi plus m 2 pi. So sine m phi is equal to sine m phi plus m 2 pi. If this is to be valid, it means that m 2 pi must be equal to 0, or it must be equal to 2 pi, it must be equal to 4 pi, 6 pi, etc. Because we know that sine theta is equal to sine theta plus 0, sine theta is equal to sine theta plus 2 pi, sine theta is equal to sine theta plus 4 pi, etc. Okay, so m2 pi must be equal to 0, 2 pi, 4 pi, 6 pi, etc. It means that not only for this one, for the negative values also it is possible. So we can write m2 pi is equal to 0 plus or minus 2 pi, plus or minus 4 pi, plus or minus 6 pi, etc. So it implies that m is equal to these values divided by 2 pi. So m is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Right? So the possible values of m are 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. We can prove the same thing if we are taking f dash is equal to n dash cos m phi. From there also we can prove that m is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. These are the possible values of m. The same we can prove by taking the imaginary set of the solution. For example, let us take the f double dash is equal to a exponential. One solution is a exponential im phi. Let us take this solution and we can check for the value of m from this solution. So the that it means that f double dash phi must be equal to f double dash phi plus 2 pi. It means that exponential im phi must be equal to exponential im phi plus 2 pi, that is equal to exponential im phi into exponential im 2 pi. It means that exponential im phi is equal to the same function, that is exponential im phi multiplied by exponential im 2 pi. It means that exponential im 2 pi, this one must be equal to 1. Exponential im 2 pi must be equal to 1, and we know that exponential im 2 pi is equal to cos m2 pi plus I sine m2 pi, that is equal to 1, because exponential I kx is equal to cos kx plus I sine kx. Like that we have written, you have learnt that in the previous semester itself. So if you are expanding this exponential function in this way, in the trigonometric way, then we can get a cos m2 pi plus I sine m2 pi is equal to 1, and this is possible only if m is equal to 0 plus or minus 1 plus or minus 2 plus or minus 3, etc. So we get the same values of m from the imaginary set of solutions as well. So we have concluded that the m can have only certain values, that is 0 plus or minus 1 plus or minus 2 plus or minus 3, etc. So obviously this m is going to be a quantum number. So this is rotational quantum number. M is the rotational quantum number. Okay, we have introduced a quantum number from the solution of the Schrödinger wave equation for the particle in a ring. And now we have n dash a as coefficients in the solutions. We don't know the value of this n dash a, etc. Obviously these are the normalization factors. Means when we are normalizing this function, we will get the value of n. Let us try to normalize, let us try to apply the condition of normalization for f. We just assume that f is a normal function, and then we will find out the value of n. So if f is normal, then it means that integral 0 to 2 pi f square d phi is equal to 1. We are taking the integral from 0 to 2 pi because it will cover the entire points on the ring from 0 to 2 pi. Then the particle will make a complete rotation. It means that anywhere in the ring the possibility to find out the particle is maximum. That possibility is 1. You will obviously find the particle somewhere in the ring. So if you are integrating from 0 to 2 pi the f square d phi, in the solution the possibility to find the particle will be equal to maximum value, that is the 1. Therefore, let us expand this equation. Integral 0 to 2 pi f square d phi. F square is equal to n sine m phi. Therefore we have n square here, that's a constant, sine square m phi, that is equal to 1, and therefore n square integral 0 to 2 pi sine square m phi, we can write it as 1 minus cos 2 m phi divided by 2 m phi. We have to put d phi also here. D phi is equal to 1, because sine square theta is equal to 1 minus cos 2 theta by 2. That I have applied that relation here. it means that n square divided by 2 integral 0 to 2 pi d phi minus n square divided by 2 integral 0 to 2 pi cos 2m phi d phi is equal to 1. That is n square by 2 integral d phi, that is equal to phi from 0 to 2 pi minus n square divided by 2 integral cos 2m phi d phi, that is equal to sine 2m phi divided by 2m from 0 to 2 pi, that is equal to 1. Therefore, n square divided by 2 into 2 pi minus 0, that is equal to minus n square divided by 2 into see, m is equal to 0 plus or minus 1 plus or minus 2 etc. We have already proven that. And if phi is equal to 2 pi, then sine 2m phi will be 0, because m is an integer or 0 plus or minus 1 plus or minus 2 etc. and phi is also 2 pi, then it will be like if m is equal to 0, it will be sine 0. If m is equal to 1, then it will be like 2 into 1 into 2 pi, that is equal to 4 pi. Sine 4 pi is equal to 0. So any value of m, for any value of m, sine m 2 phi will be 0 when phi is equal to 2 pi. Therefore, we can write 0 minus sine 0 when phi is equal to 0. Obviously, it will be 0. That is also 0. That is equal to divided by 2m. Okay, that is equal to 1. It means that n square divided by 2 into 2 pi minus n square by 2, 0 minus 0, that is 0. So this entire term becomes 0, that is equal to 1. So it means that 2 and 2 are cancelled. So n square into pi is equal to 1 and n square is equal to 1 divided by pi, and n is equal to 1 divided by root pi. So we have obtained the value of n here. So n actually is a normalization factor. By applying the condition for normalization, we have found out the value of m, that n is equal to 1 divided by root pi. Therefore, f is equal to 1 divided by root pi into sine m phi. So f is equal to, we will write this last. So we can also prove that n dash is also equal to 1 divided by root pi. We can take this function f dash is equal to n dash cos m phi and do the same calculation. Then you will find that n dash also is equal to 1 divided by root pi. And if you are taking the imaginary set, and then from there also we can find out the value of the normalization factor. The normalization factor here is a. We can find out the value of a. So in that case, integral 0 to 2 pi f double dash into f double dash star d phi is equal to 1. Here I have taken f double dash and f double dash star. F double dash star, as you know, represents the complex conjugate of f double dash, because here you can see that f double dash actually is a complex function. That is why I have taken the complex conjugate of this function. Therefore, we can see that integral 0 to 2 pi f double dash into f star, so it contains a, so it is a square into exponential, let's take exponential im phi, one function, that is a exponential im phi is one solution, or a exponential minus im phi is another solution. Let's take the solution a exponential im phi, then exponential im phi and f star, that is exponential minus im phi d phi is equal to 1. So it means that a square exponential im phi exponential minus im phi, that is equal to 1 a square into integral 0 to 2 pi 1 into d phi, that is d phi is equal to 1. Therefore, a square into integral d phi is equal to phi 0 to 2 pi is equal to 1, or a square into 2 pi is equal to 1, or a square is equal to 1 divided by 2 pi. Therefore, a is equal to 1 divided by root 2 pi. So we have obtained the value of A as the normalization factor here, that is 1 divided by root pi. So we can write the complete wave function. So complete wave functions are f is equal to n sine m phi, where n is equal to 1 divided by root pi, 1 divided by root pi, sine m phi, and f dash is equal to n dash is equal to 1 divided by root pi, n dash is equal to 1 divided by root pi, 1 divided by root pi, cos m phi, and f double dash is equal to that is equal to a is equal to 1 divided by root 2 pi, 1 root 2 pi, exponential plus or minus I m phi, where m in all these equations m is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. So these are the complete solution for the particle in a ring. Now we have to look into the energy equation, and we have already seen that in the previous video. You can see that we took m square is equal to 8 pi square I e divided by h square, that was m square. From this one we can see that E is equal to m square h square divided by 8 pi square I, m square h square divided by 8 pi square I, where m is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. So if m is equal to 0, then E0, let me write it here, we don't have enough space here. Now I will try to write everything here in this space itself, so that I can complete this video in this session itself. So when m is equal to 0, E0 is equal to 0, when m is equal to 0, because 0 into h square divided by 8 pi square I, and when m is equal to 1, actually then E1 is equal to 1 square into h square divided by 8 pi square I, and we can take h square divided by 8 pi square I, this one is as 1 unit of energy. Then we can write like 1 square, that is 1 unit, here it is 0 unit, and E2, that is when m is equal to 2, then it will be 2 square, that is 4 unit. When it is E3, it will be 3 square, that is 9 unit, etc. So these are the allowed values of energy. That is, when it can have, when m is equal to 0, m is an allowed quantum number, rotational quantum number. When m is equal to 0, it has 0 unit of energy. It means that it has no kinetic energy at all. Actually, you have to remember that in this system potential energy is 0. What we are finding out as for total energy is nothing but the kinetic energy. So kinetic energy is 0 means the particle is at rest. So for it is possible for the system to be at rest, it is allowed, and E0 is equal to 0. It means that it has no 0 point energy. If E0 has some positive value, then we can say that it has some 0 point energy. You have learned already this kind of things. For example, in the last semester you learned the vibration motion. In that case you saw that there is a 0 point energy, and in this case means that even if when the quantum number is 0, you have some positive value of energy. But in this case, when the quantum number is 0, the system has 0 energy. It means that it is at rest. So this system has no 0 point energy. But E1 is equal to 1 unit, that is a minimum possible energy, and E2 is equal to 4 times E1, right, and E3 is equal to 9 times E1. And therefore it means that only certain allowed values of energy are possible here. If the first minimum energy is 1 unit, then it is next to possible energy is 4 unit, and next to possible energy is 9 unit, right? So if the system wants to go make a transition from one energy level to the next energy level, for example, if it has 1 unit of energy, the next possible energy level is only 4 unit, means that the system cannot rotate with 3 units of energy or 3.5 units of energy or 1.7 units of energy, etc. Means the middle levels of energies are completely not allowed because of quantum mechanical restrictions. The quantum mechanical restrictions put the system in such a way that it can have only certain discrete values of energy, so the system is quantized. So whenever the particle is making the rotatory motion, not under the influence of any external force as in this case, then you can call this as a particle in a ring, and the particle in a ring can have only certain discrete values of energy, or it means that its energy is completely quantized. So this is a very simple system. We have learned how to solve this Schrodinger equation for the system, and we have reached the wave functions, the normalized wave function. These are the wave functions, and we saw that there is a quantum number involved, the rotational quantum number, and the values of the rotational quantum numbers are 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. And you have seen that the energies are also quantized. One thing that you have to notice here is that if m is equal to plus 1 or minus 1, in both cases m square is equal to 1, means for m is equal to plus 1 and m is equal to minus 1, you will have the same energy that is given. And when m is equal to plus 2 and m is equal to minus 2, in both cases you have the same energy, because m square is equal to plus square or minus 2 the whole square is equal to 4. So you have the energy equation, you have m square, therefore it doesn't matter whether m is plus or minus, it depends only on the absolute value of m. So for both quantum numbers, a set of both quantum numbers, you will have the same energy. So but you have to remember that for m is equal to plus 1 and m is equal to minus 1, you will get completely different wave functions. For example, if m is equal to plus 1, you will get 1 by root pi sine m phi, and when m is equal to minus 1, and it will be 1 by root pi sine minus phi. These are completely different wave functions, right? So even for the two quantum numbers, plus 1 and minus 1, there are two wave functions, but even if there are two wave functions, they will have the same energy. So you can call this as degenerate states. Degenerate states means there are states which are represented by two wave functions, but they have the same energy. Such states are called degenerate states. So all the levels, in this case, all the levels means not the E0, but even E2, E3, etc., or doubly degenerate for a particle in ring. All the levels are doubly degenerate, because m can be either plus m or minus m. For both values of m, there will be equal energy or same energy, but they will lead to different wave functions. For all the levels are doubly degenerate. So these are all the things that you have to learn about the particle in a ring. And it is a very simple system, and then we will extend these results to a particle in a sphere, and that's a three-dimensional problem. Now we learned the two-dimensional problem in the xy plane, then we will extend these results to the three-dimensional problem.